In this collection of videos, we're going to finally get to Galois theory, which is one of my absolute favorite things to cover in abstract algebra. So let's go ahead and let's get started. Let's start with the definition of a Galois group of one field over another. So let's suppose that F is contained in E, where both F and E are fields, and let's suppose that phi is a field automorphism of the larger field E. Then we'll say that phi is an F isomorphism of E if it happens to be the case that phi is the identity map on the elements of F. Now it's easy to see that if you look at the collection of such automorphisms of E, the set of all automorphisms that fix F, then you get a subgroup of the automorphism group of E, and it's this subgroup of E that we call the Galois group of E over F, and we denote that by Gal E over F. Now a similar definition, or a very useful dual, so to speak, is that definition of a fixed field of the automorphism group of a field. So let's suppose that E is a field and H is a subgroup of the automorphism group of E. Then we can take a look at the set of field elements that happen to be fixed by every automorphism that belongs to H. So sigma of alpha is equal to alpha for all sigma in H is how we write that formally. Then the collection of such field elements forms a subfield of E, and it's called the fixed field of H, and we denote that by fix of H. Now I'm asserting that this is a field, but it's a fairly easy exercise to convince yourself that the set that we've defined on this slide actually does form a field. So that's the exercise I'd like to give to you. Check that it's closed under addition, multiplication, taking inverses, etc. And before we get into the real theory here, I just want to do one fairly useful but basic example. So let's suppose that the field E is the rational numbers adjoining the nth root of alpha, where alpha is just any old integer. Now a ring isomorphism has to map the unity to the unity, and field automorphisms in particular are ring isomorphisms. So it's going to follow from the fact that you're looking at a ring isomorphism and that the unity must be fixed under this, that the rationals will be fixed by every single member of the automorphism group of E. So if you're looking for the Galois group of E over the rational numbers, where the rational numbers are an obvious subfield here, then that's going to be the whole automorphism group of E. Similarly, we'll have that the rational numbers are contained in the fixed field of H whenever H is any old subgroup of the automorphism group of E. Now I want us to note that since E is generated as a ring by 1 and the nth root of alpha, every single element of the automorphism group of E is completely determined by sigma of the nth root of alpha. That's not really relevant to what we did in the paragraph above, but this is going to be useful to us as we work with examples, and just for us to remember. It's kind of like when we were dealing with cyclic groups in group theory or in abstract algebra 1. All we would ever do when we were looking at group homomorphisms from a cyclic group somewhere was look at what that homomorphism did on a generator of that cyclic group, and that's what we're really getting at here. We don't really care. We know exactly what this automorphism is going to do to 1, and so the only thing of interest that it can do, it will do to the nth root of alpha. Now, as you may have noticed, there's an intimate connection between this process of taking the Galois group of a subfield and taking the fixed field of a subgroup of the automorphism group. And Galois noticed this connection as well, and he also noticed that it has some really nice properties. So that's what I'd like to discuss on this page. It's called the Galois Connection. Let's suppose that E is a field and G is the automorphism group of E. Let's write script F for the set of subfields of E and script G for the set of subgroups of G. Then what we have is we have a map that we're going to denote by phi from script F to script G, and we have a map theta from script G to script F, where we define phi of F to be the Galois group of E over F whenever F belongs to script F, and we're going to define theta of H to be the fixed field of H whenever H belongs to script G. Now what Galois noticed is that there's some nice properties that are upheld by these maps. The first one is that the first two properties are that these maps are what's called order reversing. So what we mean by that is if we have F1 and this is a field contained in F2 and both of these are contained in E, so that both F1 and F2 belong to script F, then when we apply phi to F1 and phi to F2, the containment reverses, and we have phi of F2 is a subset of phi of F1. When you say this out loud, it should make a lot of sense. If we take phi of F2, what that means is look at the Galois group of E over F2. That's the set of automorphisms of E that fix the field F2. However, if you fix the whole field F2 and F1 is contained in F2, you certainly fix F1. So we have this containment, phi of F2 is contained in phi of F1. And the containment works the other way. If we start with H1 and H2 belonging to script G, and we apply theta to them, then we also have that this containment reverses. So theta of H2 will be a subset of theta of H1. That's to say if H2 is a larger set of automorphisms of E, and it happens to fix a particular, we look at the elements fixed by everything inside of H2, then certainly some of the things inside of H2 will fix the same thing. So theta of H2 is contained in theta of H1. And these last two properties are also similar, but they deal with what happens if we kind of travel from F to G and G back to F by looking at first applying phi and then applying theta. And then similarly, if we first apply theta to go from G to F and then apply phi to go from F back to G, what's going to happen? And Galois noticed that something nice happens there as well. If you start with a field, a subfield of E, and you take phi of F and then travel back to the set script F via theta, then the original field F is a subfield of theta of phi of F. And similarly, if you start with H being an element of script G, and you first apply theta to H and then apply phi to theta of H, you'll find that H is a subgroup of phi of theta of H. Now, I have containments written there. It would be really marvelous if in those last two statements we had equality, and Galois had a special word for that. Well, I don't know if he was so vain as to call it Galois, but if we have that E is a finite extension of F, we will say that E is a Galois extension of that field in the special case that F is equal to the fixed field of the Galois group of E over F, which is to say that theta of phi of F is equal to F. So that's in that third property right here. If we happen to have equality, then something special is going on, and those are the field extensions that we're going to be interested in. Those are the Galois extensions. Now, it's important to note that Galois identified those field extensions as special because they really and truly are. So I want to do one example to show that not all field extensions are Galois extensions. And this will help us better understand that being a Galois field extension is really something special. So let's take an example. Let's let E be the rational numbers adjoining the fourth root of 2. So if F happens to be the rational numbers, then the Galois group of E over F is the whole automorphism group of E. This is sort of the preliminary example that we did earlier. However, we're going to claim that when we compute the fixed field of the Galois group of E over F, that we don't get the rational numbers. What we get is the rational numbers adjoining the square root of 2. So to see this, let's let sigma be an automorphism of E. And remember that when we did the preliminary example, we saw that sigma is completely determined by what sigma does to the fourth root of 2. Now, we don't know where it goes. Sigma of the fourth root of 2 is something, though, so let's call it alpha. And let's just look at some properties of what has to be true of this. Since 2 is a rational number, it's going to be fixed by sigma. And so we have that 2 is equal to sigma of 2. And 2, one way of writing that is that it's the fourth root of 2 raised to the fourth power. So once we do that, we have sigma is an automorphism of a field, so we can take all powers outside of sigma. So sigma of the fourth root of 2 to the fourth power is equal to sigma of the fourth root of 2, that whole thing raised to the fourth power, which is alpha to the fourth power. So we can see that alpha must be a fourth root of 2, even though we started out a priori not knowing what alpha has to be. It has to be a fourth root of 2. If we work inside the complex numbers, then the fourth roots of 2 are the real fourth root of 2, negative fourth root of 2, I times the fourth root of 2 and negative I times the fourth root of 2. Now, only the first two of these happen to lie in the field E, since E is very clearly a subfield of the real numbers, and not a subfield, well, only stupidly a subfield of the complex numbers. So what that means is E is a purely real field, all of its elements happen to be real numbers, and so alpha has to either be the fourth root of 2 or negative the fourth root of 2. No matter what, no matter which one of those alpha is, we know that the square root of 2 is equal to alpha squared. So now let's go back and let's take a look at the square root of 2, which happens to be alpha squared. And alpha is sigma of the fourth root of 2, so alpha squared is sigma of the fourth root of 2 squared. Now play the opposite trick, bring the square inside the parentheses, and we see that sigma of the fourth root of 2 squared is equal to sigma of the square root of 2. And what this whole line is saying then is that the square root of 2 is fixed by sigma, and it doesn't matter what sigma is. So from that we see that both the rationals, which are automatically fixed by the square root of 2, by any automorphism of E, and the square root of 2, both of those things are fixed by every single element of the automorphism group of E. So we know Q adjoin the square root of 2 is contained in the fixed field of the automorphism group of E, and it's pretty clear that not all of E is contained in the fixed field of the automorphism group of E, because I very much could send the fourth root of 2 to negative fourth root of 2, and that will not be the actual identity on the whole field E, even though it will be the identity on the subfield Q adjoin the square root of 2. So altogether, just to summarize, what we've shown is that Q adjoin the square root of 2 is the fixed field of the Galois group of E over Q, and so we didn't get Q back as the answer when Q was put into fix of Gal of E over F for F, and so this is an extension that is not a Galois field extension.